curves, uh, derivatives of multivariable functions, and integrals over multivariable functions. And we begin with something called a vector field. This is like a vector field is similar to a vector value function, where you use vectors inside space. The difference is every point inside that space has a unique vector assigned to it. And we use vector fields to model phenomena in physics like force fields, electric fields, fluid flows. For example, you can imagine the gravitational pull inside space is represented by these arrows. If you're at this point in space, that arrow represents where the gravity is pulling you towards the Earth. If you're a particle that doesn't really have an initial velocity associated with it, so your initial velocity is maybe 0 and you're at this point, that force field is going to pull you in this direction straight down to Earth. If you're a particle on this, say, blue line, or blue vector, it's weaker, but you're closer to the moon, maybe it'll pull you along the path towards the moon. Each consecutive vector shows you where to go in the next step. Similarly, this fluid flow through a river is represented by these black arrows. The intensity of the fluid flow is represented by the color. If you're a leaf floating in this sort of green patch, the arrows tell you where you go. If you look at the arrows long enough, you start to see that as it passes through a rock where the water isn't flowing, it starts to slow down, or maybe rushes. I can't really tell from the color scheme. But the arrows definitely double back near an eddy and circle around the rock. But basically, we think of a vector value function as a function where you pull in a point inside, say, a plane, and it outputs a vector whose initial point is that very same input point inside the plane. This is different than we thought about vectors in standard positions, because the vector over here on the left might be the same magnitude to the vector only over here in the same direction, but they don't have the same initial point because they are represented there because they are associated with different inputs in the domain. You can easily define or generalize this definition of vector field into three-dimensional space, or then you just pull points out of three-dimensional space and you get three-dimensional vectors and you're done. A slightly more formal definition lets us define a vector field by using multivariable functions for each component of the vector output. You take in a point coordinates of x and y, and then for the x component of the output vector, you get by some sort of function of x and y, and the y component of the vector, you just get by evaluating some sort of function of x and y. I have an example here where I try to define a vector value function where my x component is x times y, and my y component is y times the sine of x. These are different points inside my space, and if I plug those points, the coordinates of, say, -1 and 2, into these functions, I can get the x component of this vector shooting down according to these equations. As I move them around, you can see that I get a different vector for every single point. Those vectors are the output for the given input of the points A, B, C, and D. Now, it's convenient to see all vectors that you can get at every single point inside your plane, and you can do that in GeoGebra by put a button here. Now you can see a little sample, which is maybe called a slope field in GeoGebra, of how the vector field looks, and it sort of shows you this wavy pattern. At this point, maybe when x is equal to 0, notice when x is equal to 0, both the x component and the y component are both 0, so it's a 0 vector. But as you move away from the y-axis, where x is equal to 0, you can see that the arrows have a sort of wavy patch where they sort of point down. If you go in this direction, it gets bigger and bigger, but then it starts to change direction. That's the waviness, and it sort of levels out and then bounces back. To be clear, I'm the one moving where the sea goes, but I'm trying to do my best to follow the directions of the little arrows. So here are some quick examples of planar vector fields that you might see. Notice that this one looks like the vector fields are swirling around the center. I expressed it by having the vector field was defined by the x component being based on the y coordinate and the y component of the vector being based on the negative x component. You can see that if you match the x component with the x vector and the y component with the x coordinate, and the y component with the y coordinate of the point, you get something that looks like everything's being pulled out of the center. If you just flip the signs on the vector, value function multiplied by negative, it looks like everything's getting pulled in. And it's getting pulled in by as large as the vector necessary to get into the middle. This vector field, I have the x and y components being functions of e to the negative x squared for the x component and e to the negative y squared for the y component. And you can see a weird sort of shape when you do that. Kind of tricky. But if you did want to graph it by hand, you at least want to make sure you get several points to get a sense of what the field looks like. And sometimes there's some helpful tricks or to choose vectors that have the same magnitude. Maybe you can find a pattern of what you're looking at in that way. Other patterns might be just choose a path of points to plot into. Another pattern that might help you is to just choose another trick that might help you is to look for patterns that you see in the calculations that might give you similar values in your components. So maybe if I wanted all of this, I could make all of my y components equal to 0 if my x happens to be equal to 0. So if I choose points along the y-axis. You can systematically choose points to plot. In this case, I want to figure out the vectors for each of these pink points that I've calculated. For each of these pink points that I found. If I were to take 0, 0, I would plug into this function, and off to the side, you could see that 0, 0 gives me the vector where it's positive 2 in the x direction, 0 in the y. That would give me this vector right over here. Notice if I look at this vector field function, it actually doesn't depend on the coordinates y for how my components are defined. It only depends on the x. So as long as my x is equal to 0, I'm going to get a copy of this one vector at that particular point. So any point along the y-axis is going to give me the exact same magnitude and direction vector. If I shift my if I shift my x coordinate over by 1 unit, I can evaluate this expression. And that means it's going to be over to the right by 2 in the x direction and up by positive 1/2 in the y direction. So this vector over here. Once again, as long as I choose points that have the same x value, the same x coordinate but a different y coordinate, I get a copy of the same vector. If I plug in 2 for the x coordinate and a 0 in for the y coordinate, that gives me this particular vector. That gives me a vector that goes over to the right by 2 and up by 1. If I put a negative at the point negative 1, 0, if I substitute that into my vector value function, in this case I give it a vector that has a 2 to the right and negative 1/2 down. As long as my x coordinate is the same, I get the same value, the same kind of vector. The x coordinate negative 2 and y coordinate 0 gives me the vector 2, negative 1. And there we have our vector field. This is a nice vector field with enough symmetries that it's kind of easy to draw if you see a pattern. Usually you'll have more complicated vector fields, and in that case you can click on the link on our Canvas course page to make GeoGebra graph the vector fields for you.